So I just carried out a forecasting exercise for one of my projects, and I used a Python package called Skforecast, which is basically an ensemble package which uses a lot of different kinds of machine learning regression algorithms, but just more sophisticated. Skforecast, and you can see that I've installed XGBoost, LightGBM, CatBoost, and we are also going to do linear regression. Just a quick look at the data set. The data is very simple: Facebook spend, Google spend. Just kept it simple for this one demonstration, and we are trying to predict new customer sales. So that's the raw data set. What this model is going to do, or the modeling exercise, we're going to actually run multiple models here. We're going to try to also create time series variables, and these variables will be created in the process of the models itself, of modeling itself. So there's going to be three parts to it. The first part is model training using in-sample validation, which means that we're going to use the trend test split, which simply means that we are going to take the data set and then divide it into a training data set and a test data set, and the model is going to learn from the training data set, and then it's going to predict on the test part. So that's the first part. And the second part, I'll show the outputs in a sec, but let me show the second part, which is out of sample, which in fact the second part is this one, which is direct prediction on future or unseen data. This totally skips that intermediate step of having in-sample validation, which is an in-sample means that it's from the same data set that it was provided, which it is able to see. So that split between train and test and then predicting on the test part of the data set, that part is completely skipped here. It is going to learn on the entire data set that it was initially provided, and then it's going to apply its learnings on the future data set and try to predict on that. So the future data set is simply going to be some dates. So the data set actually varies from 1st January 2024 to 31st of December of 2025. So the new data is simply going to be January of 2026, the data for that new sale customer data. And we obviously have the spends data. We have the original new customer data, revenue data as well. So it's going to see what's the level of accuracy that this prediction models can actually get. And then finally, we have out of sample prediction, which actually combines these two approaches. We are going to do the in-sample validation using the trend test split as well, but it's also going to try to predict the future unseen data, and then it's going to measure the level of accuracy or the errors that generate. So I'm not showing the code behind it. There's obviously a lot of stuff that's going on, but the idea is that it first shows a snapshot of the data, the raw data, and then a time series plot which shows. And from this data, you can clearly see that during the months of December, or November, December, which is the Black Friday, Cyber Monday period, there are clear spikes, right? So that's very obvious. And there are also small spikes around the time of, say, July or about August. So it's around that time that this brand also gets spikes. And this is the observed data. Now what's going to do is called the STL decomposition, which is basically a decomposition of the data set, the time series data set, into seasonal and trend components. So we're going to get the trend, and then we're going to get the seasonality. Seasonality of 7 days has been applied to it, and that's why it looks like this, very frequent. And this is the residual. So the idea is that if this split between a seasonal component and a trend component is correct, then the remainder that you're going to get, the residuals, that's your deseasonalized, detrended data. And that should be fairly random, because you don't have any trend, ideally, theoretically, it should not have any residual trend or seasonal component left in it. And therefore it should be pretty random. But there are some clusters, as you can see, during specific parts of the year, which is usually the PFCM part again. So those outliers actually are still there. So it does have some seasonal effects still remaining. So that's why this requires a little bit fine tuning, where you have to probably use specific holiday specific regressors. Facebook Profit does that. It can also be done manually. The approach that I've taken is basically using dummy variable approach for specific seasonal components, which I'll come to in a moment. We'll see. Those are basically month, quarter, and day of the week. So these are created out of the data set itself, as you can imagine. So depending on which day of the week, it's going to have a dummy variable. And month, quarter, obviously which month of the year and which quarter of the year. So these are basically dummy variables that are used as variables itself. So your original raw variables, or exogenous variables as they're called in the context of Skforecast, any predictor becomes an exogenous variable because it's a time series analysis. Facebook cost and Google cost in this case, these are the only other main variables. And this part here is basically a calculation of autocorrelation. It's trying to understand whether or not there are effects of lagged variables, meaning the revenue of today, the target variable of today, the outcome of today, actually whether or not it has got some dependence on lag variables of past revenues. So revenue of 3 days back has an impact on the revenue, that the outcome that we have today. So that's basically a very typical purely time series and autocorrelation, autoregression basically. And you would not really want that. Otherwise, if it's present, you would try to do what's called a differencing, or trying to go for a stationary, try to create a stationary time series data set. Stationarity means that it is completely devoid of trends. But if that still happens, like you still have lag variables remaining, then it might mean that you have to do differencing again, first order, second order, and all that. So none of that actually has been done in this model. So you'll see that from the ACF and PSAF plots, these are basically your autocorrelation plot and your partial autocorrelation plot. And so what typically means is, if you have a gradual smooth decline for the ACF plot and a couple of sharp spikes towards the beginning in the PSAF plot, which is exactly the case here, you'll see, and all of these are significant outside of that shaded gray zone, as you can see, then what happens is, this means that there is actually a trend or an autocorrelation component. So that autocorrelation component has to be tackled by including lag variables. So this model has only one lag variable. So yt minus 1 is the lag variable which is taken as a predictor for yt. This is basically the relationship that's taken into account. So apart from these ones that I've said, Facebook spend and Google spend and month, quarter, and day of the week, we also have another lag variable, which is the previous days lag revenue variable, which is taken as an input. And now the outcomes for the different regressor models. So XGBoost regressor, RandomForest regressor, LightGBM rather, LightGBM, CatBoost, and Linear Regression. And it's a comparison between all of these. So all of these models have run, and we have figured out, which is not very surprisingly, that in this case, CatBoost actually has the best MAPE percentage, the lowest MAPE, which is mean absolute percentage error, which is probably one of the better ways to understand the accuracy level of any forecasting or an approach. This is, but it's just much lesser because we are not doing things like the transformations, saturation, or carryover effects. And then you have a MASE, which is scaled error, which simply means that if it's 1, it's just as good as naive observation, naive prediction, no sophisticated calculations like this or analysis like this, which is, if it's 1, then it's not useful, right, at all. So if it's less than 1, it means that it's doing something better than the naive calculation, the naive observation rather, naive prediction. And the lesser it is, the better. So the least in this case is the RandomForest regression. The MASE is best for RandomForest. For CatBoost, it is MAPE. So this was the first approach where we did that in sample validation, the trend test split. We also have the actual versus predicted graphs, different models. And that same table that we just saw, this is also represented in form of this nice little horizontal bar chart as well. You can take a look and it should be pretty self-explanatory. You have the base MASE value like we saw for random regressor, but for CatBoost we actually have the base MAPE value. Okay, again, the best is simply the lesser ones here. Ideally, it should be actually less than 10% MAPE. Okay, and that's why it probably requires a few more features, like I was saying, like probably the BFCM. You'll actually see from the graph also that the best one is CatBoost regressor, right? And the actual is this deep, the bold yellow one. And this CatBoost regressor is getting pretty close, but it's not still capturing the entire effect of the BFCM period, which is a massive sharp spike for the brand. So that basically requires, therefore, that is a repeated phenomena, right? Obviously the scale is different, but that's a repetitive phenomena based on at least this 2-year data set, and therefore it has to learn that, and it has to be trained using special variables, and those are holiday regressor or holiday effect variables in the model. And so that's the summary, and that's how this has been done using the in-sample validation. When we don't do in-sample validation, we directly ask the model, directly train it on entire data set, the original data set, which is, you can see for the entire training data, it is starting from 30th of January of 2024 to entire data set to the 31st of December of 2025. And the future data set is simply the first month or entire January of 2026. So that's what it's going to predict using all 702 data points as its training data. So no in-sample validation. Again, this is generally not recommended, using this and directly applying it on future data, because you don't have any idea, prior knowledge about the model itself, but it does give you that first, of course. So in the outcome part, what you will see is that it first gives you how the different models are doing, right? This model comparison now. So what has happened is you'll see that the MASE and the MAPE percentages have actually gotten better, and this is because it has trained on more data. So that's a very important point. So more data points actually help the model learn better. So it learned the patterns better, and you can see that compared to the previous case where it actually trained on a shorter period and then tried to do the prediction, the MASE values were higher. And yeah, so that's the difference between these two already that we can see. And the MAPE values have also come down. In a lot of the cases, most of the cases, it was above 20, and except for one case, it's actually all below 20. And not surprisingly, linear regression has the highest MAPE value. Okay, and best model per metric has also been generated here. We can see for MAPE, CatBoost is best, and in this case, CatBoost is actually the best for all the accuracy metrics. And this is again that prediction. Of course, the future period prediction is only showing for that part here and how each of these are doing. And you can see that the lines have gotten much closer now to the original one, which is the bold yellow one. And again, that similar table, that same table has been presented in the form of a horizontal bar chart. Very nice to see. So all the predictions for each of the single days has been given as an output here. And you have also a comparison of the different models. And again, once again, you can see how the different data metrics actually, or accuracy metrics actually look like. And then the final one is the out of sample prediction, which is where we do both. We combine both. We do the in-sample validation as well as the prediction on the future values. So this is where the model learns from the training data set. And now there's just one thing here to be noted, like this is specific to Skforecast because Skforecast actually uses the recursive method, which we just said, and the recursiveness comes because of the lag values. So yt depends on yt minus 1, and that can only be possible therefore is when you actually include all the days. So if you try to use prediction, the training data only up to say the 31st of August of 2025, and then suddenly asked it to predict January, then there would be a problem. And in general, that's also not good. So what it has done is it's going to get trained till 31st of August. That's the training data set starting from January of 2024 to 31st of August of 2025. And then it's going to predict the entire remaining set of data. Although we only want the prediction for January 2026, but it's going to do the entire prediction, and it's only going to slice it out for the first month of 2026, that's January. So it first gives the validation. So you can see there's a part A here, which is validation on the test split. And then it's going to do the out of sample validation. This is that first part. This is the same exact thing that we had got previously. Remember, these values will be the same. And you can just go and check that. The first step that we had done, actually, the first exercise where we only did the in-sample validation. And this time, this is the part B, which is where it's doing the future predictions. And one interesting thing, the rest of the outputs look very similar. You also get the daily predictions and all. Now you actually see a validation versus future summary. This is what actually gives an idea of another concept, which is called drift. Now, drift means that this allows you to understand whether your model is actually becoming affected by any drift. And the drift can be because of two things, like change of relationships, which is a model drift, a change of relationships between the variables, or the data itself has really changed a lot, not necessarily the relationships. That's basically called a data drift. So there can be an effect of either of these two things, and we can see that this is the drift basically. And there can be two types of drifts, where there's a potential overfit of distribution drift, which means that the model is actually performing worse on future data. So it did very well when it was trying to predict on in-sample data, but it's not doing as well a job when it's trying to predict the future data. On the other hand, for negative drift, it means that the model is actually performing better on future data, which means that during the in-sample validation, it was a conservative validation, meaning that it was being a little too strict about its predictive powers. It actually did a better job. And we can see that in this case, almost all the cases are negative drift, meaning that it's actually performed better on future data because the validation was probably too conservative, and it actually ended up doing a better job than it did in the in-sample validation case. And the only case where it didn't was for the LGBM, the LightGBM regressor. So that's where we actually saw that the value became more than 1 for the future MASE, which, like I said, that means that it's actually worse than even a naive observation. And the MAPE drift, and the future the future MAPE was also pretty high. So therefore, these two became actually positive, the MAPE drift and the MASE drift. So this is one approach, and each of these models can actually be improved by hyperparameter tuning, and there's a lot of other things that can be done, like adding more variables, like I said, or trying even other kinds of approaches. And the whole idea is that the forecasting is important, because whether you're in performance marketing or branding or a mix of both, having right forecasted values which are fairly accurate helps you take decisions faster, right? You can take decisions ahead of time, and you can plan your channel mix, you can plan your budget allocations, you can plan ahead for your promotions and everything. So forecasting is very important. Try to build accurate forecasting models. If you need any help with that, I'm open to discussions. But yeah, the whole point is that the forecasting is a very important exercise, and it really should be taken seriously. If you try to do this entirely using AI, it's going to be very problematic, because you really need to put in a lot of effort into understanding each and every component, and it should be properly fine-tuned accordingly. So yeah, this was what I wanted to discuss. Just wanted to show you a use case. It's a relatively simpler use case. There are more complex models that I also work on for forecasting, and but this was just for demonstration that I used a simpler use case. Any questions? Happy to engage in discussions. Do let me know in the comments. But thanks for watching, and I'll see you in the next one.